Alright, hell yeah. So this is one of my favorite problems, or just because you can guess. And so what we have is a slide crank mechanism. So this thing goes back and forth because this thing goes around in a circle. And kind of the gist of the questions are like, hey, what's the velocity of this and what's the acceleration? And it gives you an angle, you know what I mean, this 30 degrees. It's like when this is 30, what's the velocity of this? So anytime you have something go around in a circle, well, you know what I mean, figure out what the velocity at 0 is. So if this crank arm is down here, this whole thing is going to be fully extended. And I don't know if it's easy to see, but the velocity is, it ain't moving. And then when you start to pull up on this, you know what I mean, these angles are still real shallow, but they do start pulling it. And when this crank arm gets to vertical, like a 90 degrees, then the velocity is the greatest. P is being pulled almost the same. So anyway, we'll go over that. And then when you go back to the other side, then all your angles go back to kind of nice and shallow, and then this thing kind of stops and then goes the other direction. And you can get two pieces of information just by the fact that this goes around in a circle, that this has to just go back and forth. And anything that changes direction, so if you have this go this way and then it changes direction, well, guess what happens at the direction change? The velocity is going to be 0. And then that's why I said if this angle is 0 degrees, the velocity is also 0. So those two things you can pick up. And then you kind of want to know what the velocity max. So when this... And the problem says is that this spins at a constant RPM. So if you have like an electric motor, that thing's just going to go at a constant RPM. You're going to have, whatever electricity going into it, constant electricity, constant force on the motor, constant rounds per minute. It's not just going to, yeah. So anyway, so now we can actually, and they're always going to give you speed in like radians. Well, for this one they don't. It's 480 rounds per minute. But this is omega. This is typically want to get into radians per second, because kind of the equation is just like, well, I don't like radians, or what the hell's a radian? But radians times radius, that's all you got to notice. Is that radians per second, that's omega, times radius is always something useful. So just think radians times radius gives me something useful, and that's going to be the velocity of this point. So anything spinning around a circle, the point at the farthest part of the circle, at the farthest part of this radius, will have this velocity. So even us going around the Earth, let's say at the equator, we have a surface velocity of like 1,000 miles per hour. Anyway, that wasn't helpful at all. Okay, so back to this. So now we can figure out what the velocity of this point at C is. We can kind of figure out the velocity of the edge of the circle of this thing. If we get this into radians and then multiply it by the radius. So we have the radius and it's in millimeters. I would just change this to meters. So we got 0.1 meter, and then we got 0.6 meters over here. And we got plenty of time on the clock. Alright, let's get to it. So we got to take 480 rounds per minute. How many rounds per second is that? I don't know if it's obvious, but you got to divide by 60. You could do this, 480 revolutions per minute, and then just go 60, you know what I mean? You would go 60 minutes, and how many seconds is that? Whoops, I messed up, so I'm going to go 1 minute, 60 seconds. Minutes can cancel. Now I'm going to have revolutions per second. And that's 480 divided by 60. That's going to be 8 revolutions per second. Now, is that a useful? Does this give us anything useful? Well, we need to know. Like I said, we need to know what the radians per second is. So what the hell is a radian? And I'm just going to say this. In a circle, 1 radian is 60 degrees. And guess what? In a circle, you're going to get 6 radians. Because you have 6 60 degree. So if I do this circle into 60 degrees, there's 60. You get a 60. Everyone gets a 60. And guess what? You got 6 radians. Now, you get 2 pi radians in a circle. So it's 6.28 because pi is 3.14, so it's double it. See? 6, 2, 8. So it's double pi, you know what I mean? But if you just say, hey, 6, you get close enough. Because if you got 6 radians in a circle, in one revolution, you're saying that we're going to have 8 revolutions in a second. How many radians per second is that? Well, it's 8 times 6. You know what I mean? So if you think of radians in a circle as 6 and not 2 pi, it's going to be easier just to guess. So now 8 times 6, I don't do math. No, I'm going to mess that up. 8 times 6 is 48. I was going to mess that up for sure. So now we have 48 radians per second. Cool. And now we can multiply by this distance. Like I said, radians times radius gives you something useful. Our radius is 0.1 meters, so you just move the we got 4.8 meters per second. That's how fast this C is going. But like I said, it's going to be 2 pi radians. So instead of 6 times 8, it's going to be 6.28 times 8. So let's do that. 2 pi, 2 pi 6.28 times 8, you get 50.26, and then move the decimal place 1, so divide by 10, or multiply by 0.1. So the actual velocity at C is 5.03, and that's kind of what they have in the books. So booyah. So now we found this velocity at C. So the cool thing is we can answer this question just real fast now, is what's the velocity? So the velocity at P when theta is 0, when the angle is 0, is just going to be 0. And then the velocity max when angle is 90 is going to be this. You know what I mean? Theoretically, I mean we're just saying, hey, if this point's up here at a really fast speed of 5 meters per second, isn't this thing just going 5 meters per second? Sure. I mean, you do have some angles here that kind of change it just a little bit, but because this is so long and this angle is small, yeah, the max velocity is basically just 5. Okay, but what they want to know is what's the velocity at 30 degrees. You know what I mean? So at least you know the velocity at 30 degrees is going to be between 0 and 5. You know what I mean? Let's just choose 2.5, and you're not going to be too far off. Because I can actually just give you the answer right now. So here's the problem. And the velocity is going to be 2.8. Okay, so but this was just to get you in the ballpark. And I did kind of a cool way to, and then, so what we want to know, I mean, any problem where you have something go around in a circle, I need to slow down just a little bit, is circles are pretty cool. Because if I have a circle, and I have this thing going out, and we call this point C, and point C can be up here, and it can be at 30. Okay, so, like, this is why a circle's cool. Because if I go from here to here, what didn't happen? This distance didn't change. This change in x is just super small. And then when I go from here to here, you know what I mean? Now this change in x is pretty big. And if I go from here to here, the change in x is the biggest. So this is going to be 30 degrees, another 30, another 30, and this is going to be your 90. So 30, 60, 90. And then one other thing happens with the circle is because the other question that we want to know is what's the acceleration of this thing? Because some circle problems, you're going to have like a huge acceleration just right off of the get-go. Sometimes you have like a machine that like actually rapidly stops, you know, and then rapidly, you know what I mean, the acceleration is all at the theta 0 point. But on this one, not so much, because your velocity is 0, but then if your next velocity is like, you know, velocity of, you know, real high or something, if it goes from 0 to 2 meters per second in just 1 degree, then you're changing. So what is acceleration? Acceleration is going to be change in velocity, change in time. So how could we figure out what our change in acceleration is? Well, let's look at this circle. So we know right here to right here, our change in distance is just real small. And what we do know is that the omega, the revolutions per second is constant. So it's going to, if we do 30 degree blocks, it's going to be the same change in time to get from here to here as it is from here to here as it is from here to here. So the two equations that you need to use while you're doing physics with velocity and acceleration is the definition of velocity. Velocity is change in position, change in time, and acceleration is change in velocity, change in time. So the change in the velocity we're interested in is the velocity in this direction. So we're saying if this c goes from here to here in this direction, we're going to see some, you know, velocity of p. But from 0 to 30, this change in x is real small. And then the change in time is just something normal. It's going to be the same for the same time here as there. So our velocity is going to be real small. So our change in velocity is real small. And then from here to here, hell yeah, our change in velocity is actually pretty decent. Yeah, because our change in velocity is decent through here. So I mean, basically, let's say the slider just doesn't even move. So it's like our velocity is 0 right here. Let's say it gets up to here, our slider still didn't move. But then once you get from here to here, this next 30 degrees, our velocity is basically at max. So let's say from 30 degrees to 60 degrees, we're getting to max velocity. And I think you can see that because once this thing is just, So let's draw one more circle. So as this slider goes up, we're getting no velocity. This slider is going up in the circle, but then it gets to here, and then once it gets to here, it's kind of going on this part of the circle. And the velocity of this point C is consistent through the top swing of this circle. And so this slider P is already got up to max velocity right here, and its velocity didn't change from here to here. So that's the other part of this equation. You're getting up to max velocity right here of this slider, but from here to here, the velocity of the slider doesn't change. It's still velocity max, pretty much. So your acceleration, go back to the acceleration, your change in velocity, well, you're already at max. So you're already at max, so your change in velocity is velocity max minus velocity max, 0. Your change in velocity, your acceleration up here is actually, you know, pretty low. Your velocity is the most, you're going to have this thing going the fastest, but your change in velocity, there's no acceleration. It's like when a skydiver gets up to terminal velocity. That's the terminal velocity phase. And then when this thing goes over here, this slider's got to slow down. And so what we found is that the max acceleration is going to be right in this 30 degrees. So that's real important. Because some problems, the max acceleration is just right off the get-go, depending on what kind of design you have in these mechanisms. But in this one, all your acceleration is, your change in velocity is the greatest between 30 and 60. Okay, sweet. So now, that's why this problem says, hey, we want to find the velocity at 30, and we want to find the acceleration. And honestly, if it said find the velocity at 60, that would be an interesting problem because it's going to be pretty darn close to this. And we're going to find the acceleration at 30, and that we're going to get the biggest acceleration. I'm going to throw some more time on the clock. Okay, so there's one way that I like to solve these problems numerically. Since we already kind of guessed, Well, and then we can, oh, no. Let's guess the acceleration, and then I'm going to do the numerical problem probably for tomorrow. But how would we guess? We already guessed kind of like our velocity is going to be kind of halfway in between. You know what I mean? And can we do that? So how would we figure out what the actual velocity is? You know, if we think at 60 to 90 is going to be basically 5, and this is going to be basically 0. What's the velocity right at 30 degrees? How the hell would we solve that? Oh yeah, hell yeah! I remember how I did this. And then we're going to try not to even use a calculator, because what do we know about 30 degrees? We know that like 30 degrees, this is going to be like 0.5, and then this is going to be 0.866. So if you have an angle 30 degrees, this part's going to be 0.5, and this part's going to be 0.866. And if you think of these as percentages, it's 86.6%. This is going to be 50%. It's better just to think of these as fractions too, because you probably don't want to convert them to percent and back and forth. But what we have here is that this was at 0.1 meter, but now at 30 degrees, it's going to be at 0.866. So whatever point was right here, it just moved. So velocity equation, change in distance, change in time. So it moved from here to there. So we could actually find the average velocity from 0 to 30, and then let's do 60. So if we have this angle 60, now this distance is 0.5 and this is 0.866. So now our new distance is going to be and we have to subtract this, you know what I mean? And this is 0.0. You know, if this is 1 meter, it's going to be 1 meter times 0.866, which is 0.0866. And then if you subtract these, 0.1 minus 0.0866, so your change in distance right off the bat is going to be 0.0134 meters. And then change in time. We'll do change in time later, but we already know revolutions per second, and we can figure out the time for 30 degrees because we know that it's going to be 1/8 of a second to do 1 revolution. We should go over that in a second. But anyway, to get just like 3 different points, we're going to get 0 to 30, 30 to 60, and then 60 to 90. Cool. So then the next one, it went to 0.5. So you went from 0.034 to 0.5. So we're going to go 0.5 minus 0.0134. 0.5 minus 0.0134. And then we get change in x is 0.4866. And then we'll get a change in time. And then the next one is going to be basically the other part of this. You know what I mean? From 60... Because if you're already at 90 degrees, you're just going to finish this 0.5. So then it's just 0.5 divided by change in t. And now you can see the velocity at 60 degrees is pretty much the same as the velocity at 90 degrees. Okay, so now let's go over the change in time. Because any of these radians per second or spinning problems where omega, which is the revolutions per second, radians per second, revolutions per minute, you want to get into radians per second because then you can find the velocity. That's that equation. That's going to be the easiest way. You're going to radians times radius, find the velocity. Cool. But then also, it's kind of nice to have things in revolutions per minute because you can convert it to revolutions per second. Now we have 8 revolutions a second. Sometimes it's good to be like, okay, 0, 1, we're going to go, 8 times in a circle. Cool. So what's the time for 1 revolution? Well, it's going to be 1/8 of a second. And 1/4 of a second is 0.25, so it's just easy to go from 0.25. What's 1/8? 0.125. So we're going to have 0.125 seconds for 1 revolution. But that's 360 degrees. So we just want to know the time for 30 degrees. So, you know what I mean? How many 30 degrees are there in a circle? Well, if there was 60 degrees... This was 60, 120, 180, so you're going to have 12. So you're going to have to divide by 12. Or what you would have done is, yeah, does that make sense? 0.125 is the time for one revolution, and then we're going to divide by 12. And we're going to store that as alpha t. And then our time is going to be 0.010416 repeat seconds. And I stored that in my calculator as t. Cool. Okay, so now we can just find the velocity. Let's just figure out the velocity just right off the bat. So we're going to go 0.0134 divided by 0.01. So our velocity is 1.3, and I'll do t, 0.0134. Might as well get a little more accurate. So our velocity can be 1.29. For this, 1.4866 divided by alpha t. Our velocity, oh, damn it, made a mistake. Well, is this going to be right? Is this going to be right? No. This isn't right at all, because it's going to be it's going to be 0. It's going to, yeah. I think I made a mistake, because this is 0.1 meters, so this last one is 0.05. This is 0.0486. So yeah. So let me so 0.04866 divided by alpha t, and hopefully that was the mistake there. Velocity is going to be 4.67. Velocity here is going to be 5. You know what I mean? 0.05 divided by alpha t. No, it's going to be 4.8. Oh, okay. Yeah. Fair enough. Our max velocity is going to be that 5 point. Okay, yeah. So these are just average. And then, yeah, so the average velocity from 0 to 30 degrees is this, and then you have this. So I don't know. So we could just add these two up, 1.29 plus 4.67 divided by 2, and we would get an average velocity of 2.98. I mean, at least we're in the ballpark. You know what I mean? Because it gives us a second guess of what the velocity is at 30. You know what I mean? And yeah, this is a guess, and it's better than just guessing 0.25. And so what is the actual velocity? The actual velocity is 2.8. So 2.88 meters per second. So our guess isn't too bad at 2.98. Hell yeah, that's pretty much it. So that's how I did that within, just a couple. Actually, I did it pretty fast. You know what I mean? I just wanted to explain this. But what I did is I got the change in time. I just want to know the change in time for the first, 30 degrees, and then 60, and then 90. And then I used these ratios. Now, let's do it. Let me put some more time on the clock. Oh, I got to do one more thing. So that was the velocity. We kind of averaged the velocity at 30 degrees, but what's the acceleration? Same thing. It went from 1.29 meters per second to 4.67. You know what I mean? Pretty fast. That's going to be our max acceleration. So our max change in velocity is 4.17 minus 1.29. And let's just do that. So we got 4.67 minus 1.29. So we have a change in velocity. So our acceleration is change in velocity, change in time, which is 3.38 meters per second divided by that change in time for that 30 degrees is going to be 0.01. And these are an average. So if this was the average velocity between 0 and 30, that's going to be your velocity for 15 degrees. And if this is 30 to 60, 30 plus 60 divided by 2, this is going to be 45. So our acceleration is going to be kind of in between 45 and 15. So 15 plus 45 divided by 2. So our acceleration, well, yeah, that gives us pretty close. This is going to be our acceleration for 30 degrees. And our change in time is still going to be that 30 degrees from 15 to 45. 15 minus, yeah. So perfect. So now we just have a quick guess of what the acceleration. And acceleration is pretty substantial, because change in velocity is 3 meters per second, and our change in time is just tiny. Our alpha t is just 0.01. So it's it's like multiplying by 100. So 3 times 100, that's going to be 300. So let's just do it. 3.38 or whoops, I'll go back and get the actual answer. Oh, yeah, it's just 3.38 divided by alpha t. Our acceleration, is going to be 324.48, 324 meters per second squared. Now, what the hell does that even mean? It means this. Once you got the acceleration, this is going to accelerate, and this has mass. Let's say this is like a piston in a car. Those weigh like 2 pounds. Those weigh 1 kilogram. Piston in a car weighs 1 kilogram. So you use Newton's equation. F equals ma. What you did was find the acceleration. It's the most important thing in physics is to find the acceleration of a component. Because if you do find the acceleration, get a number for it, you know its mass, and then you can find the force on it. Maybe the force that you're actually going to ram something with it, or the force, in this member that you actually that needs to support this darn thing without just breaking apart. So our force is going to be in newtons, and you should always do this. 1 newton is equal to 1 kilogram times 1 meter per second squared. And this gives you 1 newton. What the hell is a newton? Well, it's 0.25 pounds. It's a quarter pound. So this is a quarter pound. Okay, so how many newtons do we have? So force in newtons is equal to, our mass is 1 kilogram. Our acceleration is, though, 324 meters per second squared. So it's the same thing, but we just have 324 newtons. Divided by 4, hell, we got 81 pounds. So we got 81 pounds of force in this, of tension in this member, you know what I mean, that's needing to pull the slider while it accelerates it through its max acceleration from 30 to 60, and then another 60 pounds of force to actually slow it down on the other side. So it's substantial. That's not a huge force. Sometimes these accelerations can blow up on you, where if this is a small mechanism with really small metal parts, the metal parts could break, and this thing would just, if it's running in a huge cycle, it could fatigue this, you know what I mean? Yes, because its acceleration can generate a lot of force with the Newton's equation. Okay, sweet. So now that's it. That's how I basically got and what the hell is the acceleration? What did they get the acceleration? So I would do this, even though that took like 30 minutes. I would do this just within the first 5 minutes and get just a rough guess. So that their acceleration right on was 253 meters per second squared. But I do not want to combine videos, and I just want to get the hell over with. So we're going to grab this sheet of paper, and I'm going to show you the numerical method of how to do these problems. All right, here we go. Okay, now, and I'm just going to do it the easiest way first, because this thing's real long. And if you just notice this thing's real long, it doesn't, the fact that this goes from here to there, this change in x is basically the same change in x here. You know what I mean? Because this change in x, I mean, look at this, look at this. I mean, trigonometry says this distance don't change. This change in x is so friggin' tiny. So what we want to do, well, this is what I do. So I get my 30 degrees, and I figure out what this distance is. Okay, so I figure out what that is, and we're just going to call it A. And then I go to 31 degrees. You know what I mean? I don't mess around. Well, no, and we'll do 31. We'll do 31, because what I would do is just 30.1. And that'll give you a better answer. But we'll do 31 first. It might make a little more sense to you. And then we're going to find this. So you know this distance is 0.1 meters. So the equation that you use is cosine. So cosine of 30 is equal to adjacent A over the hypotenuse, 0.1. And you can simplify this just by 0.1 cosine 30. When you do a lot of these engineering and physics, you just do this, 0.1 cosine 30, because I want to get this. And it's the fraction. This cosine 30 is going to be like 0.866. 86% of 0.1 is going to give you that. And we already knew that, 0.086, but I'll write it in. So 0.1 cosine 30, 0.0866. And we're going to store that as alpha A. Okay, hell yeah. And now we're going to go 0.1 cosine of 31. So we'll just get this. Cosine of 30, store this as alpha b. Perfect. So now, so what the hell did I just do there? Well, I took the distance right at 30, and you know this distance, and then I found the distance at 31 degrees. So now we can find the change in x, which is just b minus a. You know what I mean? Or a minus b. But if you go b minus a, it's a negative. A minus b. So within that 1 degree, you know what I mean, our distance changed 0.000858 meters. Okay, cool. Isn't the definition of velocity change in x, change in time? So now we just need to figure out the time for 1 degree. And didn't we figure out the time for, like what was this? This was 480 divided by 60. 480 divided by 60. This was 8 revolutions per second. So that's going to be 1 divided by 8. This is going to be 0.125 seconds. 0.125 seconds per 1 revolution divided by 360. This is the time for 1 degree. So last time we did the time for 3 degrees. This is even smaller. 0.000347 seconds. Okay, store that as alpha t. Cool. So now we have change in x, alpha. So we got alpha a minus alpha b. That's our change in x divided by t. And now we got our velocity is 2.55. You know what I mean? All right, hell yeah. So we found our velocity. Why is that so low? Well, because you do have a component from this. You know what I mean? If this is 30, this change in x is a little bit. It adds up. But let's go one step further. I mean, but this was just super fast and easy. So let's go 0.1. So if we go 0.1 degree, we're going to go 0.125 for 1 revolution, divided by 360 for 1 degree, divided by 10, store that as alpha t. Make sure to change your alpha t if you're changing your degrees. Okay, but now we're going to do the change in x, and that's going to be 0.1 sine 30 minus 0.1 sine 30.1. And then we got to reverse that, so 1 minus answer. But anyway, divided by alpha t, this gives you a velocity of, how the hell did we mess that up? Okay, so we got 0.1, 0.1 cosine, that's why. 0.1 cosine 30.1 minus 0.1 cosine of 30. Perfect. So, bummer. Yeah. I get it now. Anyway, and then divide that by alpha t. And our velocity is equal to 2.51. Oh, it's actually getting worse. But anyway, so I guess this does come into play. So this other angle over here is going to be so what's this distance when this is 30? Well, this distance right here is 0.1 sine 30, and this distance is 0.1 sine 31. So let's go back to do this one. And then when this is 31, now we know that when this long one is 0.6 meters, we want to find this angle, and ultimately we want to find this distance. And I mean, I guess oh yeah, is there an easier way to figure out these? I think you need the angle. I don't know. Maybe you don't. Maybe you don't. But no, I think you do need the angle. The only way I know how to do this is like, oh, okay, so I know this is 0.1 sine 30, and now I know this angle because, so if I go sine of beta is going to be opposite over adjacent. 0.1 sine 30 over 0.6. And then I can inverse sine this crap and then get the angle. So, inverse sine of this, and now I can get beta. And then once you get this, then you have to get the x, which is x is then you'll go cosine beta is equal to x over 0.6. I'm sure you can just use tangent. I swear to God, you could probably just use tangent, but you still got to get beta. Yep, and then your x is going to be 0.6 cosine beta. Okay. And yeah, so it makes it just a little bit tricky. And I would probably write this crap out, but anyway, let's just plug away. So we're going to get 0.1 sine 30 for this guy, and now how are we going to do this? Now we're going to go inverse sine of that answer divided by 0.6. Perfect. That gives you beta. And now if we go over here, we're going to go cosine of that answer times 0.6. And now we got our x. And we're just going to store that as d. Okay, now we're going to do the same thing for this one. So we're going to go 0.1 sine 31 to get this distance. Once we got that, we're going to go divided by 0.6, inverse sine of that, and then we're going to take that angle, which is 4.9 degrees, cosine that angle, and then times 0.6. Store that as alpha e. So now we have this. So now the velocity of this slider is actually the change. Ah, shoot, gotta throw. All right, catch you on the flip side. All right, we're back. All right, so the velocity of this slider is actually what we said. What we said it was. So it's now going to be we said it was b minus a, but now it's going to be b plus e minus a. You know what I mean? It's going to be the final minus the initial. The initial is a and d, and then the final is b and e. So let's go alpha b plus alpha e minus alpha a plus alpha d. All right, and then inverse that. So okay, so now we do have our final change in x, and now we need to divide it by the change in t. Change in t, what we wanted was just 0.125 divided by 360. So 0.125 divided by 360. Booyah! So now we have our velocity is 2.91, 2.918. Okay, 2.919. You know what I mean? So that was closer to our 2.88, and really close to just our initial guess. So that's kind of fascinating. So now let's change. So instead of this being 31, we're going to go 30.1. So now we're going to go 0.1. Well, all this stuff stays the same. A and D stays the same, but B and E changes. So we're going to go 0.1 sine of 30.1. And then we're going to throw that in here, divided by 0.6. Inverse sine that stuff. Get our new angle. It's going to be very similar, okay? And then, cosine that angle times 0.6. A lot of this is just like juggling. It's just like holy toly. And I'm not doing a very good job of actually showing. But anyway, so we got our x, and that's going to be our stored as alpha e. Okay, perfect. So now we're going to go back and alpha b plus e minus alpha a plus alpha d. Okay, and inverse that. Now we're going to divide by 0.125 divided by 360. Throw an extra 0. Oh, shoot, why didn't that come out? Ah, bummer. Bummer. All right, so we ran into an error. Yeah, and really I should be writing this out a lot more. But okay, so we're going to get the value. This first one for A is going to be 0.1 cosine 30. Cool. That's the value of A. Stored as alpha A. All right, and then for this one, we're going to go 30.1, and that's going to be stored as alpha B. All right, sweet. And yeah, we can find our original x by going 0.1 sine 30 and divided by 0.6, inverse sine that. That's our angle. And we're going to, and then once we got the angle, cosine of that angle is this. Yep. So 0.6 cosine that answer, that's going to be our x. So we're going to store that as alpha d. Perfect. And okay, so now we're going to go 0.1 sine 30.1, which is that, divided by 0.6, inverse sine that, cosine that angle, times 0.6, divided by 6 times 0.6, stored as alpha e. Did I get the other one stored as alpha d? Yep. Okay, cool. So now we have alpha, alpha a plus alpha d. We're going to store that as alpha j. And now we have alpha b plus alpha e. Store that as alpha k. So now we're going to have alpha k minus alpha j. Sweet. Inverse that. So this is our change in x. The change in x from here to here, which is now going to be definitely the change in x of this slider. And then the time frame is going to be 0.125 revolutions per 360. Okay, but we only want 1 degree, so we're going to divide by 360. And then divide by 10. Stored as alpha t. So we're going to go this answer. We're going to store that as L. So alpha L divided by alpha t. Perfect. There you go. 2.8. So we just ran into a hiccup, but you get 2.8 meters per second, which is the exact answer. So we showed that if you just do 30 to 31 degrees, you know, it's fairly accurate. We got 2.9 something, 2.918. But if you go to a tenth of a degree, that's always a pretty safe bet, because that's going to be like 3 significant digits. You know what I mean? 30 degrees, 30.1. So if you go 3 significant digits, you'll get your 3 significant. See, and that makes sense too. Hey, I want to get this to the 2.8. Because this rounded is 2.9, and that's what we got, 2.9. But we only had 2 significant digits because we only, started with 30 to 31. So this is also introducing numerical methods, and I love doing them with trigonometry, because you're always just like, well, you know what I mean? All I need to do is find this distance and how it changes in a tenth of a degree. And if I know that change is the same change as this slider, well, then I can use my velocity equation, change in x, change in t, find the velocity. And if you do this from and you can get a real accurate answer for acceleration, because we found the velocity from 30 to 31. Now we do another triangle and find the velocity from 29.9. And I guess we can do that. So if we do this, would be 0.1 sine of 29.9. Gotta throw some more time on the clock. Alright, sine of 29.9, okay, that's going to be there. And then we're going to divide by 0.6, inverse sine that stuff. Inverse sine that answer. Got our new angle. And take that new angle, cosine it, times 0.6. Okay, so now we have this new value, which we'll call alpha n. So that's our new x. So now, what was this original? So we'll call this original s, which was 0.1 cosine 29.9, stored as alpha s. So now we have alpha s plus n. So alpha s plus alpha n gives you that new starting value, that change in x, and we're going to store that as alpha x, alpha y. Okay, so yeah, let's do it. So alpha d plus alpha a minus this y, inverse answer, divided by 0.1125 divided by 3,600. Okay, so now we got 2.873. So now we have so we had that 2.8. Well, let's go see if we can find that. So we're going to store this as alpha z. And then we're going to store this as alpha v. So this is v, this is z. And now we can figure out the acceleration, just change in v, change in time. So we know that change in time is going to be 0.125 divided by 360, but divided by 10, because this is this is 360 degrees. In an eighth of a second, we're going to go 360 degrees, but we only want to go 1 degree and then just a tenth of that 1 degree. So that's where you get that number. All right, so change in velocity is basically just subtract those two numbers. So alpha z minus alpha v divided by our 0.125 divided by 360,000. And booyah, you get 240.2 meters per second squared. And that's going to be pretty much the exact answer. So this shows you that if you do numerical methods, to 3 decimal places, and that was a new one to me. It's just like, well, how accurate do you need to do? Well, you got 3 significant figures here, so it's going to kick you out an answer with 3 significant figures. And so what's the acceleration? 240. So we got 240.2. Their acceleration was 240. Well, there might be 2 things here. No, this is different. This is different. But yeah, 240 is the acceleration at p. So this said acceleration at p, 240. That's what we got. So that's pretty sweet. And anyway, and then if you use your F equals ma, you know what I mean? Holy Toledo. Let's say that's 1 kilogram. So we got 1 kilogram, 240 meters per second. And you're going to get 240 newtons divided by 4 is going to be 60 pounds. 60 pounds. And I forget actually what was our estimate on the acceleration in the first place. 320. Yeah, so that wasn't even a very good estimate. Well, no, I mean you might actually have a place in here that's higher. This 30 degrees isn't the highest acceleration. I mean, just what we did here, the highest acceleration is going to be at 45 degrees. You know what I mean? So you could do numerical methods to figure out the acceleration at 45. Just do 34.9, 35, and then 35.1. Do these triangles, find the x's. I mean, honestly, you can throw this into Excel and then do it that way and get that's probably the fastest. Because then you can get kind of a numerical equation. I mean, basically, you can just throw this into Excel and get like every single acceleration and velocity at all these points, all the degrees for this spinning. Okay, anyway, I'm about done on this one, but this was fun. And I get it. It's just a little bit wordy, and I'll get better at them. And I'll figure out what the hell I want to do. But I enjoyed this one. And so thanks for joining me. It was real small writing, but yeah, like I said, I had a fun time. We ran into one little hiccup there, but we figured it out. We took a breath. We didn't take a breath. But anyway, thanks for joining me, and guess what? That's the video.